Hello, today's video is going to talk about solving quadratic equations when the equations are written in vertex form. So it's like a way of finding x-intercepts when we study quadratic function graphs. So here are the basics. The first thing we should do when we see an equation is look at the left side and the right side and graph it. Just like every other equation we've solved. Now that we know how to graph parabolas, we can take this one, for example, which is a regular parabola, shift it to the right 3 units. So I move the vertex right 3, and then I put my parabola points down, over 1, up 1, over 2, up 4, in each direction, and that gives me a nice looking parabola. Furthermore, I could also verify that when x is 0, y is 9, so that helps. So I see that, and then the other side we get y equals 9, and it looks like it's pretty obvious. The solutions to this equation are when x equals 0, that's true, and when x equals 6, this is true. Put in 6 minus 3 squared equals 9. It works. Now, to show how algebra works, even though this is a simple equation and I already know the solutions, I want to study the algebra so I understand it. Here, I see a perfect square is equal to a perfect square, so if I take the square root of both sides, I end up with, on the right-hand side, that's easy, square root of 9 is 3. But on the left-hand side, we put the absolute value of x minus 3. The reason for the absolute value is, of course, if we don't include the absolute value, we're only going to get one solution. The absolute value is algebra's way of giving us the other solution too. So as we learned in the last chapter, to solve absolute values, we break into two choices, either leave it alone or take its opposite. So here on the left-hand side, I took the opposite of whatever's inside the absolute values, but I decided to move the negative over to the other side right away, and then I just add 3 to both sides and get 0. Here, I left it alone, added 3 to both sides and got x equals 6, which is exactly what I thought I would. And of course we can check with technology, but this one is such a simple equation there's no need to go much further. Here you can see though I've added a few layers of complexity. Without going into details about the graph too extensively, I know that my vertex is going to be at the point 3, 2. So from the point 3, 2, I would go over 1 up 1, but I'm going to go over 1 up 2 because we're doubling the y values. Instead of over 2 up 4, I'm going to go over 2 up 8, and boom, I ran into line y equals 10. I wanted to discuss the algebra, though. Sometimes students make the mistake of using the square root right away. Taking the square root of both sides, in this case, would be a bad idea, and the main reason is that I can't actually take the square root of what's on the left-hand side. I don't know how to take the square root of a sum, especially when there's all those other 2's and stuff in there. So the idea here is instead of actually taking the square root as soon as possible, we take the square root when it's best appropriate. If I look at putting in a number for x and evaluating, I would take in the number. First thing I would do is subtract 3. Then I have to square, then multiply, then add. If I want to get back to x, I'm going to undo the 2, then undo the multiply, then undo the square, and then undo the 3. So I reverse my order of operations. First thing I do, subtract 2 from both sides. Next thing I do, divide both sides by 2. 2 over 2 is 1, 8 over 2 is 4. Done. And the last thing I do, or not last, second last, square root both sides, and then solve like an absolute value. Here again, I didn't distribute the negative, rather I sent it over to the other side, and it made it really easy to solve. I can check my answer manually by putting in one of my solutions into the equation, or I could also check my solution with Desmos. I can look at the solution graphically and show the intersections are at the right x values. I could actually put the equation as is, and the Desmos will sometimes solve it for me. It says x equals 1 or 5. It gives you both solutions just like that. So it's worthwhile to spend time checking. The only other thing I'll say before ending this is just to point out that you don't have to have nice numbers in order to use this method. Sometimes when you take the square root of both sides, you're going to get some ugly numbers. The only thing I wanted to say about that is it doesn't change the process. We're still going to graph. We're still going to predict. We're still going to get rid of everything, solve for the square part. We're still going to take the square root of both sides and remove absolute values. The only difference is if I don't know the square root of 6, I'm just going to leave it as the square root of 6. I can estimate it as a number between 2 and 3. That's fine. But when I write my answer, the first thing I'm going to do is leave it in its pure form. So I get 1 plus the square root of 6, or I get 1 minus the square root of 6. And then I could use the fact that the square root of 6 is between 2 and 3 to estimate approximately these two numbers. And those approximations I got from looking at the graph. So hope you find this helpful. Have a great day.